Hi everyone. Um, we'll start.
Good evening, ma'am.
Good evening, madam.
We'll start. Thanks. Dijkstra. One example of Dijkstra algorithm, which is to use the shortest, use to find the shortest path, the shortest distance. So let's take this example. So our in this Dijkstra algorithm, the main point that you keep in mind is that we just draw the graph first. So if you have, let's say, you have this thing, you're taking a smaller graph this time. Let's say you have this thing. Then in Dijkstra algorithm, the things to keep in mind, first one is that you start with a source vertex. Let's say your source vertex is this. And then you only go to the vertices. So you consider the distance till here 0. The distance here is considered 0, obviously, because this is the source vertex. And then you only visit the intermediate vertices, the immediate vertices.
Um,
So
I have a thing like uh you numbered this edges. Is this you numbered the edges or is this some kind of
weighted
degree?
graph. We
Weight
used to
factor.
do, this is a weighted graph.
Okay, okay.
And you do Dijkstra for weighted graphs only, right? So you need a weighted graph to perform Dijkstra algorithm, which is used to find the shortest distance from a source vertex. So basically trying to find the shortest distance from this vertex to every other vertex that's there in the graph. That's our aim. That's why we're using this Dijkstra algorithm. So first thing to keep in mind is you take one vertex. So that would be given to you. The source vertex is generally given, it's given to you. And then you just take the immediate vertices. By immediate, I mean the one that has a direct edge with this vertex. You take this one and this one. It's easier if you make a table first. So if we make a table, we first write all the vertices 1, 2, 3, 4. And then first we initialize things. So to initialize, we take the distance at initialization. This is the initialization step. At the source vertex, the distance is 0, and at every other vertex, it's infinite. And then on the first step that you have, the next step, you take the vertices that are directly connected to 1. So those are 2 and 4, right? So you have an edge from 1. You can go from 1 to 2 and 1 to 4. So you consider 2 and 4 this time, and you change the distances here. So you do 0 plus 2, because this distance is fixed. Now first you fix this distance, because obviously this is not going to change, right? This is now fixed. And then you add the distances to this distance only, because you're going from this vertex to other vertices, the immediate vertices. So you add distances to the distance of this vertex. This distance is 2. So you take 0 plus 2, 2 here. And this distance is 0 plus 3, 3 here. And is still at infinity from this vertex. By infinity, when you write infinity, you mean that this vertex is not directly it does not have a direct edge. Like you can't reach via an edge from vertex 1 to vertex 2. That's why we have an infinity. And this has already been fixed in this iteration step. So you keep this one 0. And the next one to be fixed is the one with minimum weight or minimum distance. The minimum distance you see here is for this vertex 2. So now this vertex distance gets fixed. So 2 distance gets fixed for vertex 2. For vertex 1, your distance is 0. So from 1 to 1, your shortest distance is 0. From 1 to 2, your shortest distance gets fixed and it's 2 now, right? And then in this one, you fix the 0th vertex. In this one, it's this one. So you take the second vertex. Now you take B2 and take direct edges from B2. So you have this direct edge from B2, this one, and this one, right? But you can't change the distance of one now, right? Because it has been fixed. You have fixed it at 0. So there is no point changing one. That's what we mean when we fix distances or weights. So when this has been fixed, that means it's 0 now. It's not going to change. So there's nothing to change here. So you'll only be changing this one. From 2, this is the minimum weight. So you consider V2. And then from V2, you there's only one more edge, right? So this you change, and
Node
this 2
3
had
is
weight
2.
2, right? At
Yes.
2 we have weight 2. So you add to this 2 is to be added to this the weight of this one. When you are going to the next vertices, you're first fixing the weight of the current vertex, right? So you fix the weight of 2. Now this has been fixed. Now wherever you go from this vertex, you'll be adding that weight, this weight, the weight of this edge to the weight that you have here, or the fixed distance that you fixed for 2. So you have to add that to 2. So you'll add this 2 to the fixed shortest distance for 2, which is 2, right? So you'll add 2 to 2, you'll get 4. If there's a confusion, that's
No,
because
ma'am.
we have a lot of things
Vertex
that
2 is 4, vertex 3 is 4.
Yeah,
Vertex 2
but
will
it's
be
Vertex 2
2.
should be 2
3
only,
for
madam, right? We have fixed the distance, so it should be 2 only.
1 second. Let's change this weight. Let's take it 1. So at 2 you have weight 2, right? Sorry, distance 2. The shortest distance for 2 has been fixed and it's 2 now. So
Hmm.
here the distance is 2. And then if you're going to other vertices from here, so you can only go to 3, right? Only immediate vertex is 3, and you can't go to 1 because 1's weight has been fixed as 0. There's
Hmm.
no point going again. Even if you do it, you'll have 2 plus 3, 5, which is greater than 0. There is no point changing this. And you can't even change it because you've already fixed this one. You can look it in any manner you want. So you just do this change. So it will be 2 plus 1, 3, right? The last, you have to add 1, the weight of this
For
edge.
vertex 3 is 3, yes.
So this should be 3, right?
Yes.
Now this gets updated to 3 because 3 is less than infinite. You only update these weights, uh, no, these shortest distances. So you only update these shortest distances, these are distances, when you have a lesser weight. Otherwise, you keep it as same. This has already been fixed. And for 4, this doesn't change, right? Because you don't have a direct edge from 2 to 4. This remains same. Now, out of these two, you have to choose the minimum. So you can choose any one you want. Let's choose B4. So if you choose B4, now this gets fixed. And from B4, the outgoing edges are this one and this one, right? So if you change the 2's weight, shortest distance for 2 has already been fixed. So there's no point exploring this one via 4, right? We don't consider this edge. We just take care of this. So at 4, you have weight 3, this 3, and you add this 3 to this. So it becomes 6, but 3 already has weight 3. So if you compare 3 with 6, since you're trying to find the shortest distance, you should be taking the minimum of 3 and 6, which is 3. That's why we don't update it. So we don't update 3, we keep it as 3 only. And this is also 3. This is 2, this is 0. That's your final weight.
ma'am,
That's your final.
why we didn't change this V 3 for V4?
You have two choices here. You have to choose the minimum of these two. So your choices, you can choose any one. I have chosen fourth. I've chosen the fourth vertex and I fixed the shortest distance for the fourth vertex. So the distance for fourth vertex has been fixed as 3 now, shortest distance. And then you explore vertices from 4, right? So you can only explore
Yeah.
3 and 2, but the distance for 2 has already been fixed as 2. So there's nothing you can do. You can skip this one.
So we can fix the distance for 3, right? So 3 plus 3 should be 6.
If you're fixing the distance for 3, you can do that too. If you're saying I want to fix the distance for 3, that's fine. But then you don't have any outgoing edges from 3, right? If you fix this one, then you will take B3. But to update these ones, you have to have an outgoing edge from 3. That means nothing gets updated and everything remains same. So you'll get the same table.
No, ma'am, I'm asking that why we did not write 6 in the place of V3
Because we have
3.
to take the minimum. We take if you choose this one, then
Like you
V4
have
gets
chosen,
fixed.
yeah, like you have chosen V4. So V4 have a fixed to 3, and then we go to V3, and then it's 3 plus 3 should be 6, right?
It should be 6, but you only add, that's what I've been repeated for so long. You only update things, you only update these distances when they are lesser. Now you have distance 6, but you already have 3, which is smaller than 6. So we only update when we have something smaller. If here you would have gotten 2, then you would update this 3 to 2. Because 6 is bigger than 3, that's why you don't update it. We're trying
So
to
you
But
find the
check the
shortest distance.
minimum value of what is there on the table with what you calculated. Whichever is lowest, it will take that.
Yeah. Is this clear to everyone?
Yes, ma'am.
Now the Dijkstra algorithm is clear to everyone, and then we can move to the next algorithm. This one's fine. Does anyone want to ask anything from the Dijkstra algorithm?
ma'am, can we see a question based on this algorithm?
This was a
No,
question only.
no. Like in activity or somewhere like P5Q.
Yeah, okay. Are you looking for a question?
Yes, ma'am.
Do you have any question, or can anyone just, or should I take one of the activity questions on my own?
Ma'am, you can take any question of your own.
Yes, ma'am.
So this question, where you have to start your you have to use you have to start this thing from B. So you have to find the shortest distance from B to, you've been asked from B to G. in one of the questions below this. And for that, you'll need to use the shortest distance from B to G. For that, you'll need to use Dijkstra algorithm. So, and this is not directed. So let's mark the vertices first. This is B, C, D, E, F, G. And then you initialize this thing. So it's 0 here at B, and everything else is at infinity then.
A is missing.
A is not even in, okay, is here. And that's also at infinity. Starting our approach from this, so starts from here. The direct edges are this, and yeah, these three. So if this is at 0, so your G gets updated as 14. Because 14 is less than infinity, that's why you update this thing. This becomes 14 here. Then A becomes 4. And C becomes 1. And everything else is still at infinity because they don't have a direct edge with B. And this has already been fixed. Then next step, you choose the minimum of these. So the minimum should be C, right? This one. This was, you do this for vertex B, and then here for you do things for C. So from C, the distance, let me just write it here because your C, the distance for C has been fixed. So it's 1 here. And then you do things from this only. So from C, you have direct edge to A. That's it, right? Because B's distance has already been fixed, so you don't have to consider this edge. You only have this direct edge. So A's distance gets updated from 4 to 2 because this from here you'll get 1 plus 2. This one, the distance till C, and then this distance 2. So this is distance 3. And then at A, you already have distance 4. And you have to take the minimum because you're trying to find the minimum distance for each vertex. So you should take minimum of these two. So it's 3. That's why this thing gets updated to 3. And everything remains as is. Now your next minimum should be among these 3 and 14. So you choose 3
A.
next. Yeah, you choose this one. Now your distance till A gets fixed. So far, distance till B and C has been fixed. Now A gets fixed as at 3. So the shortest distance from B to A is 3. Then this is fixed. This we have fixed this time. And then fix this here actually. And then we try to update from A. So from A, there are the 3 vertices. C because has already been fixed, so we don't change this one. We don't consider this. So for these two edges, you have 3 plus 1. For F, you have 3 plus 1, 4. And at F, your distance is infinity. So you have to take the minimum of infinity and 3 plus 1, 4.
4.
So the minimum of these two is 4. So you write 4 here. And then for this one, you do 3 plus 1, which is 4. And at D, you have infinity. So you take the minimum of 4 and infinity. So you get 4 at D again. And everything else remains. You have
E will be
an edge
13.
here. So you take 3 plus 10, 13. And at E, your distance is infinity. So you take the minimum of these two to get 13. And you don't have a direct edge with G. So G remains as it is. Then next up, these have already been fixed. So you have to take the minimum from these 4, right? These 4, you have to take the minimum. So the minimum you can take, either you can take D or you can take F. Let's take D first. We're fixing this distance. Now from D, you have only one edge. We're not considering this edge because A's distance has already been fixed, so there's no point considering this one. So we take this one. Distance at D has been fixed to be 4, right? So 4 distance we have fixed, and this is 4 plus 5, 9, and the distance at F is 4. So we take the minimum of these two, which is 4 only. So we keep this thing as 4. These have already been fixed. Yeah, that's it. And everything else remains same. Because we don't have a direct edge from D to E and D to G. That's why we're not changing these two. Then we take the next minimum out of these three. So out of these three, we take the minimum to be this one. And we fix vertex F. Distance for F now has been fixed. So till F, the shortest distance from D to F is 4.
4.
So you write F here. And then from F, you have these two edges. But the distance for D has already been fixed, so you don't actually 3 edges. So you don't need this edge because the distance for D has been fixed. Distance for A has been fixed, so you only consider this thing. It's 4 plus 4, 8. And the distance for G, so you have to take the minimum of 8 and 14. So because 8 is minimum, so you should be taking 8. This gets updated. And everything else, and we don't have a direct edge from F to E. So E doesn't get updated. Then we come to the next minimum out of these two, this one and this one, because everything else is fixed. So the minimum, we take this one. We consider G first. The distance for G now is fixed to be 8. This distance is fixed to be 8 now.
Madam, we can stop here, right? We need to only find B to G. Then why to be considered G?
Yeah,
No,
we're
you have
trying
to
to do
check
the
all.
entire thing.
Okay, okay. But answer is we can get from here, right?
No, E will get
Yeah,
updated.
it's G has not been fixed yet. Even if you just want to find the distance from B to G,
Okay.
G has not been fixed yet. We've only found these distances. G has been fixed. No, we took this as minimum. Right. So you've already found the distance 8, but we're trying to complete this entire.
Okay, understood.
Okay. So these are fixed, obviously. And the next minimum is this 13 only. So do we have a direct edge from G to E? Yeah. So the distance till G was 8, and then you add 8 to 1, you get 9. And here you have 13. So you take the minimum of 9 and 13, and you get 9. So E gets updated to 9, and everything else has to be kept the same. So we get these as minimum distances from D. So the minimum distance or shortest distance from B to B is 0, B to A is 3, B to C is 1, and that we have things. Is that all right? Can we move to
Yes,
Yes,
the
ma'am.
next algorithm now?
yes, clear.
Yeah, clear, ma'am.
Next up, we have Bellman-Ford algorithm. In which things slightly. So first major difference between the Dijkstra algorithm and Bellman-Ford algorithm is that you can use this for negative weights and positive too. So negative, positive for both you can use. Whereas your Dijkstra algorithm only works for positive weights, we can't take negative weights there. So directly start with a question only, and then you can use the algorithm on the question directly. So let's take this one first, and then we can take up some other. Let's just take a small example first, and then we can take the bigger one. Let's say you have this thing. Let's start with this one. So we make a table here to keep track of everything. First, we mention on the all the vertices here, and then we initialize things in similar manner as we did in the Dijkstra algorithm. This is 0 and everything else remains at infinity. So starting your, so trying to find the shortest distance from A to B. This is used for the same reason. It's to find the shortest distance from source. Shortest distance of all vertices from the source vertex. Taken the source vertex to be this. This Bellman-Ford algorithm, you only need n minus 1 iterations. If you have 0, 1, 2, 3, 4, 5 vertices, so this will be done in 4 iterations. If you need more than 4 iterations, that means there is, we'll talk about what it means when you have more than n minus 1 iterations in Bellman-Ford algorithm. We'll talk about that case. So you do this thing and then you take the immediate. So in this one also you take the immediate vertices. That means the vertices that have a direct edge with this. So you take A and then the distance here was 0. So you'll take 0 here and you do minus 1 here in B. And at C you do 4. And everything else remains at infinity. The difference here is we used to fix the distances, right? So what we do earlier was we'd fix distances in Dijkstra algorithm and then we won't change them. That doesn't happen in Bellman-Ford algorithm. You don't fix any weights here. You don't fix distances here. We don't take the minimum here. Instead, what we do is in Dijkstra, we used to take the minimum and then explore things from that vertex. Here you don't take the minimum, you consider both these vertices because these have been the easiest way to keep in mind as to what vertex you need to explore. You should just take the ones that have been changed. The ones whose weight has been changed, you should explore those vertices. Now, in this case, B and C, the shortest, the distance till B and C have been changed from infinity to minus 1 and infinity to 4. So you should consider B and C. But right now, the distance at A is 0. At B, you have minus 1. And at C, you have 4. And then you have to consider these two vertices. And you have to take the outgoing edges from these vertices. So C does not have any outgoing edges. So you don't have to worry about that. And then B has outgoing edges, three outgoing edges. So this is, so first you consider this edge. So this gives you minus 1 plus 3, which is 2, right?
2.
And that, so you take the minimum of 2 and at C you have 4. So the minimum is 2, so you should update it to 2. Then you take this edge and the distance at B is minus 1. So minus 1 plus 2 is 1, right?
1.
And the distance at E is infinity. Then you take the minimum of these. So it should be, and then you take this edge. Minus 1 plus 2 is 1. And that you again have infinity here. And you take the minimum of this 1. These two are same. They have, because when there are no edges from B to B and B to A, right? So we don't change these. And then the weights that have been changed are, so this is kept constant. These the weights for these three have been changed, right? C, D, E. So you consider C, D, E edges, C, D, E vertices this time. Let's start with C. C does not have any outgoing edges. So you don't have to change any weights from C, right? Then we come to D. D has two outgoing edges. One is this and one is this. And at D you have weight 1. So at D you have 1. And then you add 5 to it. This is 5, right? So 1 plus 5 is 6. And at C you have 2. And the minimum is 2 only. That means you don't change this thing. And you keep this as 2 only. Then from D to B, this is, D has 1. And this has 1. So 1 plus 1 is 2, and at D you have minus 1. So if you take the minimum of 2 and minus 1, you get minus 1 only. This doesn't change either. You are done with C, done with D, and then we come to E. So for E, you have E has weight 1, right? So if you take 1 here, and 1 minus 3 is minus 2. So that this one, the weight for D gets updated to minus 2. 1 minus 3 is minus 2. And at D, you initially had 1. You here have 1, right? So weight for D gets updated to minus 2. And we don't have any other outgoing edges from E, so we're done. And now if you look at what has been changed, so the vertices whose weight has been changed this time are, this is same, this is same. So this got changed and everything else is same. And if you look at D, now if you change things from D, D has weight 1. If you will add 1 to this one, you will get 2. And B already has lesser weight, which is minus 1. The weight for B currently is minus 1. But if you do 1 plus 1, if you go via D, you'll get 1 plus 1, 2. That means we don't need to update the weight of B. This remains minus 1 only. And then what are the other outgoing edges?
Madam, the weight is D is minus 2, right? Not 1.
We have 1 here, and
But in the table, if you see, the latest entry shows minus 2, right?
yeah, that's updated here. It's minus 2 this time. You have to do it as per the last iteration. So you have minus 2 here. Then also if you do minus 2 plus 1, you will get minus 2 plus 1 equals minus 1. So you have to take the minimum of minus 1 and minus 1. It's already minus 1 here, so nothing changes. This
How you will
remains
change
as it is.
A to 1? The A
When
Ma'am, how did E become 1 from 0?
this, there are no incoming edges to A, right? So this is not going to change, right? This is 0 only. I think there was this one mark somewhere and I got confused.
Okay.
I erased the 0 and wrote 1 instead. That's a mistake. So it's 0 minus 1. And then this this was the only changed one, right? So any other outgoing edges from D, this is considered already. This you can consider. So at D you have minus 2. This is 5. If you do minus 2 plus 5, you will get 3. And at C you have 2. So you already have the minimum here. Minimum of these two is 2. So this shouldn't change. At D you're obviously not going to change. You don't have a direct edge from D to E, so this doesn't change. Then you don't have a direct edge from D to A, so this also doesn't change. So it remains same. That means after this iteration, nothing changes. That means the total number of iteration you need to do this problem is 3. In 3 iterations, you're done. So the maximum number of iterations you would need is n minus 1, where n is the number of vertices in your graph. If you have 5 vertices here, the maximum iterations you would need to get done with this using Bellman-Ford algorithm are 4 iterations. You need maximum 4 iterations, but we got done with Bellman-Ford in this particular example with only 3 iterations. Is this okay? Is the method clear to everyone?
Can you repeat some with some other example?
Yeah. So the main difference between Bellman-Ford algorithm and Dijkstra algorithm is in Dijkstra algorithm you fix weights. That means each time in each iteration you fix weights, but here you don't fix weights, right? You keep changing weights, and this is for negative weights. The Dijkstra algorithm, I mean, this is not particularly for negative weights, but it can be used for negative weights. Whereas Dijkstra fails when it comes to negative weights. And the third, yeah, these are the major differences. In
Here we
Dijkstra
don't
algorithm,
fix.
you, one second.
We
Hold on 1 second. In Dijkstra algorithm, we used to take the minimum of these two, right? And then we used to explore that vertex. But here we don't do that. We explore both of these vertices, right? We carry along both B and C. we don't just use B to explore further. And we're not fixing any weights here, if you've noticed. So this is the major difference between Bellman-Ford algorithm and Dijkstra algorithm. And Bellman-Ford algorithm has to be repeated n minus one number of times. There should be, this is first iteration, this is second, this is third. Now, if you're doing it more than 4 times, that means there is a cycle in your graph, a negative cycle, not a cycle. That means you have a negative cycle. We'll come to the negative cycle part later. Or should I just explain it here only? So if sometimes what happens is you are not able to get a solution or get the optimal solution using 4 iterations or n minus 1 iteration. So here the maximum number of iterations should be 4. And if you exceed 4 iterations, let's say you had another iteration here where weights changed, then another iteration here where weights changed again, that means each time you get a better shortest distance, right? Then that means you have a negative cycle somewhere in your graph. Negative cycle means the total weight of that cycle is negative. It's this thing. Let's say you have B, C, D. And if this edge is minus 4, this edge is 1, and this edge is also 1, then the total weight is minus 4 plus 1 plus 1. Now you have a cycle, and the total weight of this cycle is negative, right? It's minus 2. This is called a negative cycle. So if you're getting more than 4 iterations here, more than n minus 1 iterations, and you're each time getting a better, in each iteration, you have different better shortest distance. These are shortest distances, right? That means you have a negative cycle in your graph. Because each time you'll go through that cycle, if you have this cycle, then each time you'll go through this cycle, you will get shorter distance, right? Minus 4 each time will reduce the distance. That's why if you don't get your optimal solution or the shortest distance that you're looking for in n minus 1 iterations, that means you have a negative cycle in your graph. Let's do one more example.
Ma'am, I have a question. What does the negative weight implies?
Negative weight does not imply anything as such. It's just for you to see that if you take things to be negative, let's say if you this is some path and if you go through this path, then you gain 1 rupee. Let's say from here to here you lose 4 rupees. That means you have to pay 4 rupees. And if you gain 1 rupee here on this path, or cross this, come from this to this via this edge, you need 4 rupees, let's say. And that means you'll have to pay 4 rupees. But if you go from here to here, someone's offering you 1 rupee, then you use minus 1 here, right? You can't be using 1. There has to be some distinction between what you're getting and what you're giving. So that's to imply those things.
Okay, so it's basically opposite of the condition of the positive. Okay.
Madam, one doubt I have. Suppose if I am given with the negative weights, so can't I use the digestive algorithm to find the shortest path? Or I am bound to use this only, Bellman-Ford?
Bellman-Ford is used for negative ones. Even if you have one weight which is negative, you can't use the Dijkstra algorithm.
Okay. And how about if I have all the positive, can I still use the Bellman? Because
Yeah, this is for both positive
it is
and
more
negative.
efficient, I think, right? It's in n minus 1, I can get. No, I have only positive weights. So still can I use the Bellman-Ford because I will be getting result faster, right?
No, it's not. It actually depends on the graph. Sometimes Bellman-Ford algorithm is easier. Other times your Dijkstra algorithm is much easier.
Okay, so it will be given to us like using which algorithm we
And
need to
this,
find shortest path.
yeah. And this
Okay.
one just looks easier because your graph is easier here. In Dijkstra, we took a little complicated graph, I guess.
Okay.
Okay. And let's come to this one. This example.
Ma'am, I have a doubt.
Yeah.
So you were saying in this Bellman-Ford, we don't fix the distance, just we explore them.
Yeah.
Okay. So that's the major difference between the Excel algorithm and this algorithm, Bellman-Ford.
Yeah, that's the main difference. And there's one more difference too, because you're not fixing anything in Bellman. Then in Dijkstra algorithm, we used to take the minimum out of these, right? And then we only explore C, and we'll fix the distance, the shortest distance for C as 1, right? That is what we used to do in the Dijkstra algorithm. But here we don't do that. Here you have these two. You're not taking minimum. You're not fixing the distance for B. So we don't do any of it here.
Okay.
Uh, Ma'am, can't we say that if in a graph there are no negative weights, then Bellman-Ford and Dijkstra will be same only?
No, they're not same, because I've just discussed that in here they'll work the same way. But here you fix them even if you don't have, even if you do Dijkstra, if you do Bellman-Ford here, you won't be, what you do here is you fix the distance for C as 1, and then you only connect to vertices that are directly connected to C, right? You only go to those vertices and change the distances for them here. You don't change the ones for A, right? But in Bellman-Ford, you change for both of these. So the ones that are directly connected to A, you change the distance for them too. You change the distance for the ones that are directly connected to C. Whereas here you fix and then you decide which one to take, right? Not same.
Yes, ma'am. But in Bellman-Ford, we only change because the distance can change because of the negative weights only.
Yeah, eventually you will get the same things only, and you wouldn't have to. That's what I said. It might become similar to this one, but the approach and
Yes,
the
ma'am. But approach
algorithms
is
are
different,
different.
but it will look similar only. As that was.
Yeah. Yeah. Let's consider this graph, and let's first write down all the vertices: 0, 1, 3, 4. Initialize things from, let's say, 0. This will be 0, infinity. Then in next step, from here you can go to two vertices, 1 and 7, right? So the distance for 1 will be 10. 0 plus 10. You'll get 10 here. And this will be 0 plus 8, 8 here. No, this is the seventh vertex, right?
7.
8. Everything else is at infinity. Then you go to these two vertices, 1 and 7. So
Ma'am,
1
I
has,
have a doubt.
yeah,
So we can like 0 to 7 is the shortest distance as it is 8, while 0 to 1 is 10. So we should take 7 only, right?
these are vertex numbers. This is V0, this is
No,
V7,
no,
this is
no.
V1. Yes.
I'm saying that the 8 thing, like you have
The
written on
weight.
the edge 8, that is the weight.
Yeah, this is
Yeah,
the
so
base.
this is 8, and for 0 to 1, it is 10.
You
The weight
don't
is
take the
10.
minimum from these two. When we discussed Bellman-Ford algorithm, I said you take the minimum of this thing and the one that's already in your table, the last column that you've written. I'll
Okay.
explain that thing again. Wait. Let me just move to the next iteration, then you know what I'm talking. So first you take 10 and 8, and you write these distances at 10 and 8. When I say minimum, I mean not in these two min, not to take minimum of these two. Then in next iteration, now you have B7 and B1, right? Or 7 or 1. So from 7, there's only one outgoing edge, which is this one, right? So you update the sixth one. So at 7, your weight is 8, right? And this edge is 1. So you should do 8 plus 1. and at 6, your distance already. You just have to look at this column. Forget about the previous columns. You have to check the last column that you've written. This is the last column, and the distance uh, till 6 is infinity. So the distance that's already there in the table is infinity. And since we have to choose the minimum shortest distance here is the distance is till 7. So far is 8. And then 8 plus 1
9.
is 9. So you have to take the minimum of 9 in infinity. That is the minimum that I was talking about. You have to take the minimum of these. The one that is already in the table, this one, and the one that you get from the direct edge, right? Becomes this gets updated to 9. And then what other edges do we have? From 7 we don't have any other outgoing edge. This edge we've already used. We don't have any other outgoing edge from V7. Then we come to V1. From V1 you have two outgoing edges, 1 and 2, right? These two outgoing edges. So at the shortest distance at V1 is 10. Here the distance is 10 currently because this is your last iteration. So it's 10 here. Then you add 10 minus 4 to 10. And you get 6, right? 10 minus 4 here. And so the distance till this is 10 minus 4, 6. Right? So the distance at 6, the sixth vertex is 6. And the distance already given at 6 is 9.
9.
So we should update it again because this is 6 and 9. So the minimum that we should be taking is
6. Vertex 6. But you'll go 6.
wait. Okay, just 1 second. A lot of confusion is coming from not writing the weights. Let's write the weights. The last vertex, here we have weight 0. Then at second we have 10. Sorry, at first. And at 7th we have 8. These are the weights that we have so far. Then we first explore things via this. So this is 8 plus 1, 9. And we take the minimum of 9 and already there is we take 9 here. Then we take this one. This edge, right? So we do 10 minus 4, 6. And we take the minimum of 6 and we don't take this one because this column is not yet complete. So we take
Ma'am,
the
I have
minimum
a
of
doubt.
6 and it, yeah.
So we can't visit 10 from V1 from 6, right? We only we can visit from 6 to 5, but we can't visit from 6 to V1 as there is
Yeah.
no, I mean, no direction. So how we go to, how we visit V1 here?
What?
I'm saying we can visit
From
6 to 5. There is a direction between 6 to 5, but there is no direction between 6 and V1. So we can't go from 6 to V1.
We're not
Ma'am is
going
doing
from 6
V1 to
to
6.
V1. We are going from
So
V1
V1
to
to 6.
V6.
So should not. Okay.
Okay. What we do here is you just look at the vertices that are directly connected to your vertex. So V0, you are directly connected V7 and V1. And then you did these things. So for V7, the only connected vertex is V6. And we've already done that, right? Then for V1, and it's the question that I had initially had this arrow. Let's take this one only. Yeah. So we did this thing. Here we had 8 weight 6 and 8 plus 1 is 9. And then we take the minimum of 9 and the last column 1 is infinity. 9 and infinity, we get 9 here. Then after, now we're done with V7, right? There are no other outgoing edges from V7. It was only this edge. Now you come to V1. You have changed V1 and V7. Right? So you look at the direct edges from V1 and V7. Outgoing edges from V1 to V7. So V7 we have already done. Now we come to V1. This is V1. So the outgoing edges are, there's only one outgoing
V5.
edge, which is this. So this is 10. Here we have 10 and here you have 2, right? So you add 2 to 10, you get 12. And then at 5, you have infinity, here. You have to check in the last column. And then you take the minimum of these. So your weight, this weight gets updated to 12 because 12 is less than infinity. And no other outgoing edges from B7 and B1. So everything else remains same. So this remains 8, this remains infinity, 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 10 and 0. And let's change our weights to if there have been changes. This is 8 only. This is 10 only. This is 0. 9 and 12 are the new weights, right? For 5 you have 12. For 6 you have 9. Is still this part clear to everyone? Is the basic
Ma'am,
algorithm clear to everyone?
I did not understand from 6 to 5, from vertex 6 to vertex 5, how it is become 12.
We've not,
Not
this
from
has
6
not
to 5.
become 12 from
It's
6
1
to
to
5.
5.
This, it's from here to here. The vertices that have, you only consider vertices whose weight has been changed. So this, the weight of V1 has been changed and V8 has been changed from here to there, right? And then to construct this column, what you do is you consider V1 and your focus is at V1 and V7. So first we come to V7 and we explore the vertices that have an outgoing edge from V7 to that vertex, right? So V6, V7 has an outgoing edge, right? Let's look at the outgoing edges from V7 and V1. So let's first try to look at V7. V7 has only one outgoing edge, which is this. The weight at
Yes,
V7
ma'am.
is to be checked from this column, right? The last column is this. This is what we're constructing. So for this column to be constructed, you need the previous column. So in previous column, your weight for V7, for V6, your weight for V6 is infinity, right? And your weight for V7 is 8, right? So this weight is
Yeah,
8 and you add 1 to it. And then you take the minimum of these two. The new weight, 8 plus 1, 9. And the previous weight, which is infinity. So you get 9. 9 is clear, right?
yeah,
Now
ma'am.
we're done with V7, right? There are no outgoing edges from V7. There was only one outgoing edge, right?
Yes, ma'am.
This was the only outgoing edge. Now you come to V1. Then for V1, it's here. You, this is your last column, right? So the weight for V1 is 10. And then there's only one outgoing edge from V1. This is incoming edge. This is also incoming. This is also incoming. There's only one outgoing edge, which is this one. So the weight at V1, as per your last column, this column is 10. And this edge has weight 2. So it's 10 plus 2, 12 for 5. That's how you get 12 for 5. And you have to take the minimum of this new weight that you've got for 5 and the previous weight for 5. Previous weight you check from the last column, right? So 5's last weight is infinity. So you take the minimum of 12 and infinity. Is that okay?
Yeah, ma'am. Now I got it. But I have a question that why we did not visit vertices 1 from 6? Like there is uh,
Only have to visit vertices from this vertex and this vertex. That's it.
no, from
Because
6
only
to
these weights.
V1,
What?
like -4. From 6 to V1, we have a weight -4.
That's in the
So why
next
we do?
round. That's when you take the next one as 6 and
So
5, which you updated in this round.
You only visit the vertices, you only explore the vertices that whose weight has been changed. So the only for one vertex, first vertex and 7 vertex has the weight been changed from infinity to 8, infinity 10. Every other weight has been kept the same. That's why you don't do these things. That's why I've written, especially here I've mentioned that we only explore V1 and V7. That's
okay, ma'am. So we have to go from V1 to V5, not V6 to V1.
no, why would you go to V6 when V6 is not even been updated yet? V6 itself is at infinity right now. It has not been visited yet.
No, it has been 9, right?
It's visited in this one. No, we're making this column as per this column.
Okay, ma'am.
So to make this column, you only consider weight. Forget about this. When you're constructing this column, forget any weight that you write in this column. Only use the weights from this column, the last column.
Okay, ma'am.
Okay. So you come to the next one. Now your next updated ones are the only updated. This sixth has been updated. Fifth has been updated. Seventh is still the same. Second is these three are same. This is also the same. This is also same. So you only have to explore these two this time. V6 and V5. Now you come to V6. And there are two outgoing edges from V6. So we'll do them one by one. We have to this time we have to do V6 and V5. Let's do V6 first. So for V6, this is an outgoing edge and it has weight. So your weight at 6 is 9. And
9.
this is minus 4. It's 9 minus 4, 5. And this V1, the weight for V1 here is 10. So you take the minimum of 5 and 10. Is this part clear how you take the minimum? You take the minimum of the one that is already in the table. So for V1, this is 9 minus 4, 6. So your updated weight for V1 can be 6 if it is less than the weight that is already in the table. The weight for V1 already in the table is
5,
10.
ma'am.
5.
Yes, ma'am. 5.
So 5 is less than what is already in the table. That's why we update this thing. And in the next step, so this becomes 5. This is 0 only because there are no edges directly from V6 to V0 and V5 to V0. Right. Then this is an outgoing edge. So it's 9 minus 1. 9 minus 1 is 7. And at 5, the weight is 12. So the minimum of 12 and 7 is 7. That's why we write 7.
8, ma'am.
Thank you. We have 9 here and 8. 9 minus 1, 8. Then we come to V6.
5.
V5, right? So V6 has already been done. V5 is, there's only one outgoing edge, right? This
Yes,
is an
2.
incoming edge. So there's this thing only. And in the last column, V5 is 12. So you consider 12 only. Don't consider 8. So for this is 12 and 12 minus 2 is 10. And this is at infinity because 10 is less than infinity. So you should update this 10. And no other outgoing edges. So everything remains as is. Coming to the next one. Now the weights that have been changed are these are same. So this time the weights for V5 and
V1.
V2 also.
V2 is also changed. V2 and V1. These have been changed this time. So we'll explore them one by one. Let's start with V5. So V5 you have at V5 your weight is 8. 8 minus 2 is 6. So you should update 2. The weight for 2 is 10 and 6 is less than 10. So you should update it to 6. Then no other outgoing edges from 5. So 5 is done. I'm coming to V2. For V2 you have the weight for V2 is, so currently the weight for V2 is 10. And 10 plus 1 is 11. Weight for V3 is infinity, so you can update this to 11. 10 plus 1 is 11. Weight for V1 is 5, so don't update this one. Keep it as 5. You don't have a direct edge from V5, V2, V1 to V0. You don't have a direct edge from anywhere to V0, so you can just keep this as 0. Right. And then V2 is also done. Coming to V1. V1 has an outgoing edge to 5 and that's it. So the weight for V1 as per the last column is 5 and then you add 2 to it, so you get 7 for V5. But V5 has 8 here, so you can update it to 7. And everything else remains as is. Because there are no direct outgoing edges from V5, V2, V1 to the ones that have not been updated. Now the weights that have been changed are, this is changed,
2, 3, 5.
then 3 is also changed and 2 is also changed. Then you do these vertices V2, V3 and V5. So from V2, now the weight for V2 is 6. The current weight is 6 for V2. So if you do 6 plus 1, you'll get 7. So we don't update it. We already have 5. You do 6 plus 1, you get 7. We already, okay, we can update this thing. So for V3, we can update to 7. And then we come to the next vertex V3. For V3, there's only one outgoing edge, which is this. And the weight for V3 is 11.
11.
So 11 plus 3, you get 14.
14.
And this is at infinity, so you can choose the minimum. The minimum of 14 at infinity is 14. That's why we've updated this one. And no other outgoing edges from V3. So V3 is also done. Then V5, there's only one outgoing edge, this one. And the weight for V5 as per the last column is 7. So 7 plus minus 2 is 5. And the weight for 2 is 6. You can update it to 5. So also 5. And others are kept the same, right? 7, 9, 8, and 0. How many iterations have been done? 1, 1, 2, 3, 4,
6.
5. So we count them as, this is the initialization only. We don't count that this as an iteration. So 5 then. Coming to the next item. This time, the vertices whose shortest distance has been changed from the previous time are, these
V2,
are
V3, and V4.
V3 and V4. So let's start from V2. V2 is here. So the weight of for V2 as per the last iteration is 5, where you have weight 5 this time. So 5 plus 1 is 6 for 3. So you can take the lesser one here. And 5 plus 1 is 6 for V1. And we already have a lesser value 5, so we don't update this one. We keep V2 constant obviously because there's no, okay, let's not come here. There are the edges there. V2 is done. Then coming to V3, V3 has only this edge and the weight for V3 currently is 7.
7.
So it's 7 here and 7 plus 3 is 10. So for V4, you can update it to 10 because it's lesser than 14. Then we're done with V3. Coming to V4. V4, currently the weight for V4 is 14, not 10. Don't take as per this iteration. Take as per the last complete iteration. So it's this one. The weight for V4 is 14. 14 minus 1 is 13. So for 5, it's 13, but we already have a better thing here. Let's keep it as 7, 9, and 8. And since we're done with all of these, so these also remain same. Then this time the updated ones are
V3 and V4.
V3 and V4. Yeah. So for V3, this time the weight is 6. So we do 6
6.
plus 3, 9 for fourth vertex. We can update this as 9. And then for V4, V4's weight is 10.
10 minus 1.
And 10 minus 1 is 9. So this one we are better here. So let's keep it as 7 only. And everything else remains same. This time the updated ones are, there's only one updated, right?
V4.
So the one that has a direct edge here is with V4 is this, right? V4's weight currently is 9. And if you do 9 minus 1, with 9 minus 1, 8. And the weight for V5 is 7, which is better than 8. So it remains this way. That means we're done. Then the final weights are these. So the shortest distance from 0th vertex to first vertex is 5. To second, you have 5. These are your shortest distances. From 0. Is this okay?
Yes, ma'am.
Okay. Then can we move to the next algorithm that we have?
Yes, ma'am.
Next algorithm that we have is Floyd-Warshall algorithm.
Ma'am,
Ma'am,
Let's use
before we,
sometimes. Yeah.
ma'am, before we go ahead, this cycle in this thing, in the last iteration, it has gone from 9 to 8, right? Should we really consider that? Or how will we know, like, if we have entered a cycle?
You know you've ended, yeah, about the cycle thing. So when you have, this has 8 vertices, right? How many vertices do we have here? 7, right?
8
Yeah,
vertices.
Yeah, we were starting with 0. So
8.
we have 8 vertices. The total 8 number of vertices. So if you cross more than 7 iterations, that means there's a negative cycle. So if you repeat this one more time, if you want to, you can try and repeat it one more time. You get the same iteration here. So that means you only have 7, these number of iterations only, which is less than 8. That means there's not a negative cycle. But in the case of negative cycles, you keep getting better solutions or better distances. So that means this is 0, first, second, third, fourth, fifth, sixth, seventh iteration. And then, so you can only have 8 minus 1, 7 iterations, right? Now, if in the next iteration you get 0, 4, 3, you get better distances, 6, 9, 7, 8, 9, 8, right? Better, you got better distances, right? Better short distance.
Okay.
That means you have a cycle. That means this will
Okay.
keep getting better each time. You can't stop anywhere.
So maximum is n minus 1 times.
Maximum you do it minus 1 times. If it doesn't have a negative cycle, then on the n minus nth time also you'll get the same thing. These
Okay.
values won't change in the next iteration. If they do change in the next iteration, that means you have a negative cycle and you're never going to get an answer.
Okay, got it. Thank you.
That's also the way you detect negative cycles in your graphs. Also helps in detecting negative cycles. So
And also, ma'am, if like a vertex doesn't have like a in degree, then it will be always 0, the distance.
yeah, this does not, like this one does not have an end degree.
Yeah,
The
like if we
distance
have
is,
more than one, then they all will have 0.
no, the distance, 0 distance is, if you have a vertex here and you say that let's,
Yeah, it does
if
not have
this
any.
was the vertex, if this was this thing, then this vertex does not have any incoming edges, right?
Yes,
So
correct.
that means this you can't visit from here. So you won't be asked to find the shortest distance from 0 to 2 because you can't even reach from 0 to 2, right?
Yes.
That won't be a question.
Okay.
The distance then won't be 0. Actually, it will be infinity. If you can't reach from 0 to 2, that means the distance 2 is at infinity distance from 0. That's what we do in the table too, right? We write infinity for the vertices that cannot be reached from the present vertex. That's why we write infinity, right?
So that infinity will be constant in that case, right?
Yeah, it will remain constant because you can't reach it, no? That's why you can't update the, weight for that vertex or the distance for that vertex.
And ma'am, one more thing. Here we got like 9 iterations, right?
So these are not nine iterations. This is first, second. This is just the initialization. This step is not an iteration. This is just initialization. So your iteration starts from here. 1, 2, 3, 4, 5, 6, 7. There are only 7 iterations.
Okay. So it doesn't matter if we have a cycle in the graph, but we will still have n minus one. It's just not has to be negative cycle.
Yeah, it shouldn't be a
Oh,
negative cycle.
okay, got it.
Coming to the Floyd-Warshall method. This method is to find the shortest distance from all the vertices to all other vertices. So it's like shortest distance in pairs. How do you find the, let's take this graph only. How do you find the shortest distance in pairs means shortest distance from 1 to 2, shortest distance from 2 to 4. In this way, we're talking about shortest
Can we
distance.
do this algorithm with negative weight?
Negative ones, I I'm not sure. I don't think it works for the negative weights. It's for positive weights only. So let's say you have this thing, and so you start with the we start this thing with an intermediate vertex. Intermediate vertex in the sense, first we draw this matrix A naught. We consider this matrix A naught and we write the entries. This is the adjacent matrix for this graph. A naught is nothing but adjacent matrix for the given graph. So this first entry will be where 4, right? So your first entry is 0. The diagonal entries are 0. And then from 1 to 2, it's 2. From 1 to 3, it's 1 to 3, we don't have. Because 1 to 3, we don't have an edge. That's why we keep this entry as infinity. Distance from 1 to 3 is infinity. Direct one. By our direct edge, it's infinity. Then from 1 to 4, it's 3. Coming to 2, from 2 to 1, it's 3. From 2 to 2, it's 0. From 2 to 3, it's 2. From 2 to 4, we don't have an edge from 2 to 4. That's why it's infinity here. Coming to 3, from 3 to 4, we have 3 to 1, we don't have an edge, so it's infinity. Then from 3 to 2, we don't have an edge, so that's also infinity. From 3 to 4, it's 4. And from 4 to 2, it's 6. 4 to 1, we don't have an edge. 4 to 3, we don't have an edge again. This is your adjacency matrix. The next matrix that we make is this matrix. What we do in this matrix is, these are not powers. The one that I'm writing here, these are not powers. These are just notations. So to construct this matrix, what we do is, we take for the ijth entry for this matrix, we take the minimum of A naught ij. A naught ij means if you want the ijth entry, you should be looking at the minimum of the ijth entry from this matrix, and A naught I1 plus A naught 1j. Now what does this thing mean? This thing is the distance from I to j, considering 1 as your intermediate vertex, right? A naught ij, what does this represent? This represents, if this is 3, then what does this mean? This means that the distance, the direct distance, the direct edge from I to j is of weight 3, right? This is what Aij, A naught ij equals to 3 means, because this is an adjacency matrix. And then this means A naught I1 plus A naught 1j means this is the distance from I to 1 via the direct edge, and this is the distance from 1 to j via the direct edge, right? So we take the minimum of these two, which means we're taking the minimum of the distance of I to j directly, or I to 1 and then to j. We're taking the minimum of these two distances. This one and this one, taking the minimum of these two distances. That's how you construct A1 matrix.
Madam, how to find this I to 1? Like I to j is okay, the direct edge, but how to find this I to 1 distance?
I to 1, let's say you have A1, you have to find A1, 2. Right? You have to find this. That means you have to find the 1, 2th entry of A1 matrix. So what you do is you take A naught 1, 2. So where A naught 1, 2 is 2, right? 1, 2th
Okay,
entry, A naught is 2. And then you find A naught 1, 1 plus A naught 1, 2. So A naught 1, 1 is
0.
0. And A naught 1, 2 is 2, right? We did this here. That means that's also 2. So if you take the minimum would remain 2 only. So you can take 2, right? That's how you could take. Ij is arbitrary here. You can have
Okay.
numbers here. This is the general formula. That's why I've written Ij. And we are taking 1 as intermediate vertex. That's why we're representing the matrix as A1. So the 1 here is the matrix when we take 1 as the intermediate vertex for every Ij. Similarly, if you do A2, that means when we take 2 as the intermediate vertex for every 2 vertices. For Ij, the intermediate vertex will be 2 for constructing A2. We'll come to that later. Let's do this one first. If we want to construct A1, that means we're keeping 1 as the intermediate vertex, where this is the adjacency matrix, right? So these two you have to, if you are taking 1 as intermediate vertex, so obviously you can't take entry 1, 1, because then you'll do 1 to 1, then 1 to 1. That's why we don't take anything that starts from 1 and ends with 1, which means these ones. We don't take these ones. We keep these as, to construct A1, we keep these as constant and this as constant. So these ones remain the same. And you just have to find these entries. So this is A23. To find A23, you take A naught 23 and A naught 21 plus A naught 13. Minimum of these two, right? A naught 23 is, this is 2, this is 3, so this it's 2. And A naught 21 is 3. So it's already 3, you don't even have to check. 3 plus something will obviously be greater than 2. It's, okay, let me just write it down. 3 plus A13. A13 is this infinity. So 3 plus infinity is infinity only. So the minimum should be 2. That means this entry A naught, A1, 2, 3, this entry should be 2. So we take 2 here. Then we do the same with this one. This entry is A1 of 2, 4. So A0, 2, 4 is, this time you'll do A0, 2, 4, minimum of A0, 2, 4, and A0, 2, 1 plus A0, 1, 4. So A0, 2, 4 is infinity, and A0, 2, 1, this is 2, 1, which is 3, and 1, 4, which is 3. So it's 6. This should be 6, right? This entry will be 6. Then coming to this one, this is A1, 3, A0, 3, 2 is infinity. And then you have to do A0, 3, 1. A0, 3, 1 is this. Infinity again. So A0, 3, 1 is also infinity. That means this will not get updated. This will remain infinity. And coming to this one, this vertex, this is A1. This remains infinity. This is A1, 3, 4. So 3, 4, you take A0, 3, 4. A0, 3, 4 is this 4. Minimum of A0, 3, 4 and A0, 3, 1. So 3, 1 is this infinity. Infinity plus something will remain infinity only. So you take the minimum and you take 4 here. Similarly, you complete this and do you want me to complete this entire matrix? So can you guys do this thing? You just have to use this formula.
Okay, we can do it, madam.
Okay. That's how you find A1. One is this one represents if we take one as intermediate value. So for every ij, you're doing so your ij at entry, what does A1 ij represent? A0 ij represents the direct weight from I to j, right? And A1 ij represents the weight from I to 1 and 1 to j. So you're taking one as intermediate vertex. That's why we're taking one here. That's what this one represents. Now let's find A2. If I write A2 here, that should mean that this time I'll take 2 as intermediate vertex and compared to what? So this graph, obviously we have a graph corresponding to this matrix, right? And we have a graph corresponding to this matrix too. So let's just consider this one now. So for A2ij, the formula that we have is minimum of A1ij and A1I2 plus A1j. For A1, we did A naught here. We were taking the for A1 you consider this matrix. For A2 you consider this matrix. Yeah. A1 you take the intermediate vertex to be 1. For A2 you take the intermediate vertex to be 2. Rest everything else is same. Is this okay?
Ma'am, so we have to take that like in sequence only, right? We cannot skip any.
Sequence.
Like after A2, I cannot take A4. I have to take A3 only.
No. This it doesn't actually matter. So what we're doing is we have 4. How? Okay, let me just complete this thing. Then I'll come to what you're saying. So then you construct A2, and A2 will be constructing from A1, right? You need A1 to construct A2.
Yes.
I hope you can construct A2 the same way we constructed A1 using A0. You have to construct A2 using A1. The difference is this time you will be considering this matrix to get this matrix, and the intermediate vertex is through this. Previously, now it's 2. Then you do A3, then you do A4. Now you stop at A4 because you only have 4 vertices, right? Now this matrix that you will get will give you this. Let's say this is 1, 2, 3, 4. This matrix has zeros here. Let's say you get this matrix. That means this is your
Ma'am,
shortest
your
distance.
voice is breaking.
Is it still breaking? Better now?
Yeah, now it's fine.
Okay. So if you get A4 equals to this, that means that this shortest distance from this vertex, from this to this vertex. This is B1 vertex and this is B3 vertex, right? The shortest distance from B1 to B3 is 3 because you get A4, 1, 3 as 3, right? The shortest distance is decided by this matrix. Now your question was, do we need to take the vertices in order? Do we need to take first vertex, 1 as first intermediate vertex, then 2 as second intermediate vertex, 3 as next intermediate vertex? So you don't have to take. Also, when you're constructing, let me I have clarified this thing. But when you're constructing this thing, when you're constructing A2, you take the intermediate vertex. When you construct A3, take the use this matrix, A2 matrix you use. So for A3 ij, let me just write. Or should I just write a general formula for AN? Your AN ij is
Yes,
minimum
ma'am.
of AN minus 1. You use the previous matrix, ij, AN minus 1. And here you take I, intermediate vertex is this, plus AN minus 1, N, J. This is how you construct all the matrices. And you have to construct 4 matrices because you have 4 vertices. Your final matrix gives you the shortest distance from each vertex to every other vertex. Now, if you take them in different orders, let's say we started with 1 as intermediate vertex, then we took 2 as intermediate vertex, then 3, and then 4. Now, you can take 4 as first intermediate vertex. That means the first matrix that you would be constructing would be the matrix where you construct 4 as intermediate vertex, right? First, you can construct this one, or first you can consider. So what I'm trying to say here is you can change the vertices orders. That's fine. You can take the first intermediate vertex to be 4.
Okay. So next one will be with respect to the previous one.
Then you can take any other. It doesn't have to be there. Doesn't have to be a specific order. We followed this order 1, 2, 3, 4, but you can take 4 as the first intermediate vertex. Then you'll get a matrix, right?
Yes.
And then you can take the next vertex to be 2, or you can take it to be 1. Then you make the next intermediate, the next matrix. But you'll have to use this matrix for the next matrix.
Okay. Got it. Yes, ma'am.
And then for the
Ma'am,
next one, you can take 3. Yeah.
so in case of A1, the first row and first column will be frozen. For A2, the
Yeah.
second row
That,
and second column will be frozen, like that, right?
yeah. In this one, we freeze the diagonal is always kept to be the same. It's always 0, 0, 0. And in this one, so to construct this A1, you freeze these two. First column, first row. To construct
Okay.
the second one, you construct second column, second row. For third one, you freeze third row and third column.
Okay.
This
So
will go until n minus 1, no?
Sorry, what?
This will be continued till n minus 1.
Yeah. This if you have 4 vertices, you continue, you do it 4 times.
And one more thing.
Yeah.
If we want to make A4, then it is necessary to make the previous all previous ones like A1, A0, A2, A3.
If you are doing it in this order, then yes. Okay, we have followed this order. First, we took 1 as intermediate vertex, and then the matrix we named as A1, right? Then to make the next matrix, we're taking the second vertex to be this. Second intermediate vertex we're taking to be 2. So to construct this matrix, you need 1 matrix. But if you will follow some other order, let's say I want to take the vertices in this order, then I'll first make as per this. Then I'll use this
so,
matrix to make the next one.
so the formula changes, like instead of an minus 1, it will be changed to an.
Yeah, but these things will change. The only thing that you have to keep in mind is this matrix is the previous one, the last that you constructed, right? So you're constructing this as the first matrix, taking 2 as the intermediate vertex. Then A4 should be using the last matrix. Now, these things will obviously change.
But how
If you're
can they
taking,
construct A2 without A1?
okay, you had this graph, right? Let's say I decided to A2 means,
Like we have A naught. Now we have to create A2. Then without A1, can we create that?
yes, you can. A2, this just means that you have to take 2 as intermediate vertex. So just the way you constructed A1 from A0, if you're following, if you're if you have planned to follow this order, that I'll be taking 2 as my first intermediate vertex, then 3 as next intermediate vertex, then 1 and then 4. Then you can just simply construct A2, but this formula then would change. So first you'll construct A2 from A0. The way you constructed, how do you construct A1 from A0? You consider 1 to be the intermediate vertex and you apply this formula, right? A0 ij, minimum of A0 ij and A0 I1 plus
Ma'am, but then it
A0
also
1
requires
j.
A1 of I and J, right?
1 second. This is what you use for A1. Now, if you have decided to go by this order, then you will not be constructing A1 first, you'll be constructing A2. How do you construct A2 first? You will be doing the same thing here. A0, because you have to construct using this matrix only. Ij, A0 I2 plus A0 2j. This will give you A2. Then the next matrix, let's say you want to go to this vertex X. This has to be the next intermediate. You want this to be the next intermediate vertex. Then you will do this thing. A, because your last matrix constructed is A2, right? So you will use A2 here. A2 J plus intermediate vertex has to be this one. And this matrix has to be the last matrix that you construct. Now, to avoid confusion and to have like a concrete formula, we follow this order 1, 2, 3, 4, so that we can have an order here, right? We can make a general formula a n minus 1. Is that okay?
Yes, ma'am.
Yes, ma'am.
So, I think that is all. If you guys have anything to ask, you can. Otherwise, we can end the session here.
Ma'am, can you repeat this algorithm?
The Floyd-Warshall one,
Yeah.
did I just quickly go through it, or do you want me to explain the entire thing from the start? Floyd-Warshall is
Like we
basically
can, yeah. We can also take one question, right?
question. It's we already started with a question only. This was the question.
Okay, okay.
But we didn't solve it entirely because it's going to take time. First, we'll construct this matrix, then A1, then A2, then A3, then A4, and then you stop there. That's why we're avoiding that. That's it.
Okay. So yeah, ma'am, just give me a quick recap. So
So, if you've been given a graph and you have to find the shortest distance from every vertex to every other vertex, you use the Floyd-Warshall method. And for Floyd-Warshall method, first you construct this matrix. This is nothing but just your adjacency matrix. So this you take as adjacency matrix only. Then you construct A1. Now when you have vertices V1, V2, V3, that's why to avoid confusion, any confusion, we take them in this order only. So you start with the first vertex and you take that as intermediate vertex. That means this is the formula that you have for it. So if you're constructing A1, you take A1 ij as the minimum distance in your previous matrix. So this is because this A0 is the adjacency matrix. That means what distance is this? Is there anyone who can tell
Direct
me
from I
what
to J.
distance is this one? Sorry, what?
Direct distance from I to J.
Yeah, direct distance from I to j means if there is an edge from I to j, then this distance, this direct distance is a naught ij, right? And then you have a
If
naught
ma'am,
a1 plus,
okay, so if it is weighted, for example, if the weight is 8, then also it A not IJ.
yeah, a naught ij is the adjacency matrix for the graph, right? How do you construct adjacency matrix for weighted graphs? You write the weights here. So if you have your a 1/2th entry for an adjacency matrix, 1/2th entry would be the weight from first vertex to second vertex. So if this is 8, then your 1/2th entry, this entry, second entry in the first row should be 8, right? That's what A naught is. Were you asking something else? Okay. So this is the formula for all the entries for the matrix A1. What you do here is in A naught, if you have a matrix A naught, let's take a 3 cross 3 matrix only this time. So you keep diagonal is 0, 0, 0 only. So you keep the diagonal constant. You keep the first row and first column constant. And you change only the entries that are not on the diagonal, not on the first row and not on the first column. So you only change these two entries in this particular case. As per this formula, this is the formula that you have to use to change the entries in A1. So to make A1, keep this column as constant, the same as A naught. Keep this one as
How
constant, the
will,
same as A naught.
yeah, I have a question.
Yeah.
How will we identify that we have to just keep that vertices, like keep that column you have mentioned?
In A1, you have to keep the first row and first column constant, and the diagonal is always constant. It's always 0, 0, 0.
In A1,
Yeah,
we have to keep the first and second,
first
first row
row,
and
first column.
first row, first column constant. Okay.
In A2, now for constructing A2, you'll require the previously constructed one, right? So because you constructed A1 first, you need to use A1. To construct A1, you're using A naught. To construct A2, you need to use A1. And in A2, while constructing this, you keep the first, now in this one, you keep the second column and second row constant. Constant as the last one. So if A1, this was A1, then to construct, if this was A1, to construct A2, you keep this as constant, and this diagonal as constant. So you only change these entries that are not on these. And you use this for that. Is that okay?
Ma'am,
Yeah.
you said that for A1, A2, A3, and all, these numbers are the junctions through which we consider the intersections. So is it actually dependent on is actually A2 dependent on A1? Can't we do A2 without A1?
You
Are you
That's
sure?
what I said. You can do A2 without A1, but if you're following this order, if you have decided that first I'll take the intermediate vertex as one, first
Okay.
vertex, I'll take first intermediate vertex, then I'll take the second intermediate vertex as 2, and the third one as 3, and the fourth one as 4. Then you should be going in this order, right? First, you should
Yeah,
construct A1, then you should construct A2, then you should
yeah,
construct
but
A3.
yeah,
Yeah,
but when you are doing A3, you can
yeah.
actually have the A0 to do the A3, right?
What?
You don't have to do. You don't have to. You don't need A2, right? To do
If you're
A3.
doing it in this order, then you need for A3, you need A2. But to construct a new one, you need the last one.
Uh,
So you need A2 for that. To construct A4, if you're doing it in this order, you need A3.
Can you explain why we are freezing these columns and
Ma'am,
If
rows?
you
in A1, you have like what you draw, that is second column and first row. But you said that we have to freeze the second row and second
Yeah,
column.
it's mistake. It's a mistake. Second column in second. So, is that fine now?
Okay. Okay. I think I just got misunderstood. So
Okay. Yeah, you're keeping these ones as constant because when you construct A1, you're doing I to 1 and then 1 to j, right? Now, if you have 1 entry, or if you take any entry on the first row, let's say you're taking 1, 2. So you take 1 to 1 and then you will do 1 to 2, right? Now, for 1 to 2, if you take 1 to 2 only, then what's the point? Because you add these two and one you take directly from 1 to 2. So you have to take the minimum of 1 to 2 or 1 to 1, then 1 to 2. Obviously, this is going to be the minimum, right? Now, if you want to do these things for these entries too, you can, but there's no point. You'll be wasting time. That's why you can keep these entries constant. Is that okay?
Yes, ma'am, noted.
Okay. So anything else that anyone wants to ask?
Yes, ma'am. I have a question. It is actually from an activity question. It's about Bellman-Ford. If we have sorry, if our source vertex has an out degree of 0, so how would we compute distances from it?
What your source vertex? Can you repeat this thing?
Yes, ma'am. In Bellman-Ford, if our source vertex has an out degree of 0,
Okay. Then everything is, you're saying that there's no out degree. That means if there are any edges from A, they are the incoming edges, right? That means
yes,
you
ma'am.
can't reach anywhere from A. That means everything is at infinity only. If you, then there's no point performing Bellman-Ford. You can't even start
Yes,
with
ma'am.
it.
So, ma'am, in activity question, the answer says that in only first iteration, it will stabilize the distances
Stabilize
through
the
Bellman-Ford.
distances in the sense because you'll only get infinity, right? There's no point doing other
Uh,
iterations because you get infinity each
yeah.
time. So
Yes,
there's no
ma'am.
how.
Distances wouldn't change. How you cannot reach from there.
Yeah.
Okay. Thank you, ma'am.
Anything else?
Ma'am, what are we gonna do in next class?
Um, we'll do some questions. If you guys have any doubt, you can ask that. Important topics. Try to do uh, the Prim's algorithm and that thing. We've done only algorithms only in this week. So you have Prim's algorithm, then the second one, Pascal's algorithm, the minimum cost spanning tree, minimum cost spanning tree. Do this one. Will be questions from here, minimum cost spanning tree, and um, this algorithm, the last algorithm that we've done, we don't have questions. Not many questions are asked from this algorithm, so it's not a very important thing. Then the last algorithm that we've done, then Dijkstra algorithm, and please do that DFS thing.
Ma'am, Dijkstra and Bellman-Ford also.
Yeah, the normal. Okay, we can. Do we need to have a class on, like? Do you guys have doubts from this week? Have you tried questions from this week?
ma'am, there is Kruskal algorithm.
We did Kruskal's algorithm in last class, right?
Okay.
Has anyone tried questions from week 11?
Yes, ma'am.
You've been able to do questions, right?
Yes, ma'am.
Okay. we can discuss the important things and all in the revision sessions. We're going to have revision sessions, I guess. We can discuss it there. And other important things that I feel are important, I've already mentioned these things. Okay, now if there's nothing to ask or no other doubts, can we end the session?
Ma'am, just can you tell once that the algorithms you said, no, those which are important, you said Prim's, Kruskal's, and is there the two algorithms, the Bellman-Ford's and the Dijkstra,
Yeah,
on the
this
important?
Dijkstra algorithm and Bellman-Ford do that too.
Okay, ma'am. Thank you,
There are
ma'am.
no questions from, I mean, you won't be having questions from this this one that we just did. And
Okay, ma'am.
other four algorithms try to do those ones.
Okay, ma'am. Thank you.
Okay. Thank you guys. Bye.
Thank you, ma'am. Good night.
Thank you, ma'am.
Bye bye, ma'am.
Thank you, ma'am.
Thank you, ma'am.